Hello, AP Stats. Today we are talking about a lesson called Measures of Relative Standing. And what this will allow us to do is describe the location of data inside a distribution. Okay, so what this would entail would be collecting a bunch of data and then wondering where a certain piece of data fits in among all the rest of the distribution of that set of data. Okay. Don't worry about this. This is what we would have gotten if we were in person. Okay. So we're just going to go through this slideshow. So a couple things you need to know about notation. For this, remember we have two symbols that mean sample. We have x bar and s of x. Okay. Remember x bar is the sample mean and s of x is the sample standard deviation. And then for population, we have population mean and population standard deviation. And those are the ones that we're going to use today in our lesson, the ones I'm circling in green. So remember the one that looks like a cursive U, that's population mean, pronounced mu, and then the circle with a little tail on it, that's sigma, and that's the population standard deviation. Okay, so just wanted to set those apart for you. Remember, we'll use the sample notations when we've taken a sample from a population, and we use the population symbols when we have an entire group of people with something in common. Okay. Now, when we're describing a location and distribution, we're going to use two scores, or two methods. One is called a z-score, and one is called a percentile, or percentile rank. So these are used to, if you look at the top paragraph here, to compare values from different data sets or to compare values within the same data set. Okay? These can be used for things like comparing ACT scores with SAT scores. Okay? And we know that on the ACT score, the scale is a 36-point scale. And on the SAT, the scale is 1600. So it would be difficult to compare someone's scores just based on their score itself. Like if you had an SAT score of 28 and an SAT score of, let's say, 1200, like hard to compare when they're on different scales, okay? But with z-scores and percentiles, these will give us tools where we can compare two distributions that have different, they're made on different scales. So first we're going to talk about a z-score. And this is probably amongst the most important formulas you're going to learn this year. We're going to use it a lot. And throughout the rest of the course, we'll be using it. So a z-score is simply an observation minus the mean divided by the standard deviation of the distribution. Okay. This is the one formula we really have this in this section of the unit that you have to remember. Okay, and I'll copy it again down here. So the x value, that's the observation. That's the data point that we'd like to learn about, like figure out where it is in the distribution. The mean is obviously the population mean, okay, which we'll get that by finding the mean of the data. And then we have the population standard deviation, which we divide by. Okay. This is called a standardized score, in that it gives us a score that is relative to the position of the piece of data, which then would allow me to compare it to maybe the z-score from a different distribution. Okay, so a z-score is the number of standard deviations that a given observation x falls above or below the mean. So notice in the equation, we're going to find out how far is our piece of data from the mean, and then we're going to divide it by the standard deviation. So we'll find out how many standard deviations we are away from the mean. If the z-score ends up to be positive, it means that our data value was above the mean. If our z-score ends up to be negative, that means our observation was below the mean. Okay. So, just to reiterate, a positive z-score indicates an observation above the mean. A negative z-score indicates an observation that was below the mean. And a z-score of 0 means that the observation that we looked at was the mean. And z-scores have no units, okay? Kind of like, we would not say feet, we would not say inches or anything like that. The units of z-score is actually the standard deviation. Okay, because it tells you how many standard deviations you are away from the mean. So here's an example I'd like to go through. It says the average number of dice pulled from a bucket of dice during the AP Stats dice grab of 2019 was 27.4 with a standard deviation of 6. Okay. Find the z-score of someone who pulled 36 or 35 dice. So back in 2019, we had an ice cream bucket full of dice, and we had each kid reach their hand in the bucket and grab as many dice as they could, pull their hand out of the bucket, and then we counted. And then we made this little chart that you're looking at. It's a dot plot, okay? You can see the highest person grabbed 39 dice, and the lowest amount was 18, and 2 people grabbed those. So that's where this data is coming from. So I averaged all those out, and the average person grabbed 27.4 dice. And then I also found the standard deviation was 6 dice. So now what I'm curious about is finding the z-score of someone who pulled 35 dice. So my z-score equation is x minus the mean divided by the standard deviation. You'll want to memorize that equation because that's the only equation we have. So the x is the number of dice that I'm wondering about. Like, where does 35 fit into the distribution? So I would put 35 there. Then we always subtract the mean, okay, which it said the mean was 27.4. And then the standard deviation, sigma, was 6. Now be careful when you're doing this on your calculator because you got to follow the order of operations. Okay, you should do 35 minus 27.4 first. And that gets me 7.6 divided by 6. And then I want to do 7.6 divided by 6. And I get 1.27. So the z-score for 35 dice is 1.27. Now, what that means is that 35 dice was 1.27 standard deviations above the mean. So 35 dice was 1.27 standard deviations above the mean. So I know it was above the mean because it was positive, okay? If I had done this calculation and gotten a negative z-score, that would tell me that I am that many standard deviations below the mean, okay? Moving on to the next slide. So this was the calculation. Your observation minus the mean divided by the standard deviation. And in symbols, remember, we're going to get really good at these symbols. It's x minus the mean divided by the standard deviation. And then you can see when we did the calculation, we just filled in the numbers. If you want to do this in one shot on your calculator without doing it in 2 separate steps, like doing 35 minus 27.4 and then dividing by 6, you would have to put the 35 minus 27.4 in parentheses so that the calculator knows to do that first, and then you could hit divided by 6. So anyway, I get 1.27 was our z-score. Now, just to go over the interpretation one more time, the person who pulled 35 dice out of the bucket was 1.27 standard deviations above the mean number of dice pulled, which happened to be 27.4. Okay. If somebody else had pulled a certain number of dice and I calculated their z-score and I found it to be 1.36, let's say, I would know that this person pulled more dice than this person because their observation was further above the mean. It was 1.36 standard deviations above the mean. So I can compare how different people, how many dice they pulled by looking at their z-scores. the higher the z-score, the more dice they pulled. And the lower the z-score, the less dice they pulled. Okay? Now, percentile rank. This is another way we can compare values within a distribution or compare values in two distributions that have different scales. So a percentile rank stands for the percent of the observations that are less than or equal to it. Okay? So a person with an IQ in the 75th percentile, or the 75th percentile rank, has an IQ that's as high or higher than 75% of the population. You've probably heard of percentile ranks before. Anytime you've taken a standardized test, like an ACT, SAT, any state testing from Minnesota, they always report to you your percentile rank, so you know how you did compared to everybody else. And a 75th percentile is very good. It means only 25% did better than you, and you did as good or better than 75% of the people. So a percentile rank is another good way to show your position inside a distribution. Finding a percentile rank is not hard. What you need to do is have an ordered list of the values. So that's very important. Okay, you have to have a list that's in order. And these values right here are in order. It says scores on a recent quiz are listed below. Your score is highlighted with the red circle. You got a 71. What percentile do you fall into? Well, to do this, one thing you need to do is count all of the data that were in the class. So when I did that, I found out that there were 20 total observations. So I just counted like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, etc. Counted them all up, okay? Then what you need to do is count from your observation, like the 71, all the way down to the lowest piece of data. I need to know how many observations were equal to my score or less than that. So I'd start counting at 71 and say, I'll change colors here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 observations were less than or equal to our score of 71, and there were 20 total. So to find the percentile rank, I simply take 20 divided by 12, and that was 0.60, which puts me in the 60th percentile. Okay, so you need to find the value you're interested in. So we were interested in what the percentile rank of 71 was, and I need to count how many pieces of data were equal to 71 or less. Okay, then I need to take that number and divide it by the total number of pieces of data. Okay, and that gets you your percentile rank. So your interpretation would be, you scored the same as or better than 60% of the students in your class. Okay. Special note, if there are multiple points with the same value, you'd count them all in the calculation. So if there had been another 71 in this problem, I would have counted both of them, okay, if I'm looking for the percentile rank of 71. So if there's multiple values of the value you're looking for, you need to count them all in your calculation, okay? But this would be another great way to compare things. Imagine you had an ACT score and the person was in the 78th percentile, and let's say you had an SAT score and someone scored in the 81st percentile. You would know that the SAT score was better because they're in a higher percentile. They scored as good or better than 81% of the people, where on the ACT, that person only scored better than or equal to 78% of the people. So percentile ranks is a good way to compare distributions that have different scales as well. Okay, so why do we standardize like this? Z-scores and percentile ranks. Okay, we do it to be able to express distributions on a common scale. So if you're comparing two distributions like the ACT and the SAT that are on different scales, Z-scores and percentile ranks both allow you to compare scores from the two tests, okay? And this allows us to compare distributions.